All right, this is going to be page 1 of notes 5 of the Calc AB Notes, and we're going to talk about something called the mean value theorem. So it says it right in the first sentence here. I'm going to highlight it anyway. It's really hard to explain just how important. That's a really skinny highlighter. Let's try that again. That's better. Just how important this theorem will turn out to be. So we are going to use this theorem a ton this year. Once you learn it, it's like everywhere. So make sure that you get on top of it really quickly. When you have questions, make sure you ask them. Seek out additional help, like whatever you need to do. This is one of the big ones. This is MVT. We already know IVT, intermediate value theorem. We know EVT, extreme value theorem. But this one, MVT, this is the one you use this all the time. All right, so also use it in conjunction with IVT like frequently. So be on the lookout for that. All right, first thing we're gonna do, draw 3 interesting, I initially thought that said intersecting. I was like, draw 3 intersecting, okay. Interesting continuous curves that connect the points A and B. Label them 1, 2, and 3. I feel like this calls for different colors. So interesting, what's an interesting curve? Well, I mean, you gotta start with this. You don't have to, but that's what I've chosen to do. Maybe a sine type thing. Like this, and then maybe I got to use the bottom, right? So maybe just well, I mean, is this interesting? Probably not. Something like that. Okay. Now for each of my curves, I have to say if the curve is differentiable or not. So I should label them 1, 2, and 3 according to this. 1. I don't remember. Oh yeah, I did like 1 and then 2 and then 3. All right. Good to go. Supposedly. All right. Number 1, definitely not differentiable. Look at that sharp turn there. So if you have a sharp turn, not differentiable. Number 1 is not differentiable, so not diff. Number 2 is a sinish curve. It is definitely a smooth curve, or it is intended to be. Number 2 is differentiable. So number 2, differentiable. So far, so good. So far, we haven't been really asked to do anything. And number 3 is also definitely differentiable because it's basically a quadratic-ish or maybe a semicircle. So there we go. All right. Now, for each of your differentiable curves, label at least one point at which dy dx equals 0. So this almost feels like one of those weird magic tricks where like if you drew differentiable curves, there is no way that you won't be able to find this. So including if you drew a horizontal line from A to B, the derivative is 0 everywhere. So you would actually find an infinite number of points at which this is true. So that is not an exception to this. All right, so let's see. Here's a point. Here's a point. Here, I put my 2 like right on top of it. And then here's a point. Okay, so I found a bunch. And then for this one, there's probably only one. I mean, I feel like the intention. Ugh, what? Yeah, well, that's a horizontal, right? So we did it. Okay, what about our not differentiable one? We couldn't do it? Like maybe we could have. You could draw another function, like make it all like sinusoidal, like curling from A to that maximum, and then sort of sinusoidal going from the maximum to B. So it's like there are points where it happens, but it turns out if it's not differentiable, there could potentially not be any points. And that's probably the big takeaway that we're looking for. Let's try it again. So in this problem, A and B are on the same horizontal line. So maybe that had something to do with it. In this case, they're not. So let's roll it back. So I'm going to make them just differentiable. So, and like, I'm going to make them not super exciting because I don't want to spend like my entire life finding points. How about we just do like this? And then what if we do like this? I feel like if I had thought about this more, I could have made that picture look a little more interesting, but I did not. And I'm supposed to label them again. So 3, 2. I don't know why I'm labeling them in the color. Like, you could probably easily follow it without that, but that's what I'm doing. Oh, crud. What? I forgot that I was like labeling backwards. Okay, 1, 2, 3. State if it's different. They're all differentiable because that was the choice that I made. They're all differentiable, right? No sharp turns, no cusps. So a cusp, remember a cusp looks like kind of like that. None of those. All right, so now what's this saying? For each of your differentiable curves, label at least one point at which dy dx equals f of b minus f of a or b minus a, where b is the x-coordinate of b and a is the x-coordinate of a. You're guaranteed to be able to do this. Okay, so I'm going to sketch that in. So this is going to go like here to here. Okay, so let's see. For curve number 1, I feel like maybe here, if I draw a tangent line, something like that, looks like it works. We're just estimating. Here, I feel like kind of works. So this again, as if by magic, you are able to do this for each of these differentiable curves. So we're able to find a place where the slope of, if you look at it, this thing right here is the slope of the tangent line. And then should I label that? Let's do this. Slope of tangent. And then let's do a different color. And this is the slope of the secant line. So put a little key in here. Slope of secant. I never really used highlighters until I started using this iPad to take notes, and now like highlighters are amazing. The thing I don't like about them in the real world, like in the physical world, is how the paper gets like wet and then like kind of wrinkly sometimes, and like you can't control. That doesn't happen here, and I really like that. All right, so in each case, when we had a differentiable function, we were definitely able to find a place where the slope of the tangent line equaled the slope of the secant line on the interval. That's very cool, and we could do it in every case. Like draw the craziest function you want. As long as it's differential, it's gonna work. That's basically what the mean value theorem says. So we're gonna define it on the next page, and we're gonna do that in the next video. But basically, the mean value theorem is saying that we are guaranteed to be able to find a spot if the function is continuous on the closed interval from a to b and differentiable on the open interval from a to b. We're guaranteed to be able to find a spot where the slope of the secant line is equal to the slope of the tangent line. That's a very cool result. That's the mean value theorem. So I'm going to come back. I'll repeat that like 75 times in the next video, and I will see you there when we'll probably also start doing some problems. So that'll be good. So see you then. And now I'm going to stop this video. So I'll be back in the next one.